Welcome back. In this video we'll continue working in section 4.2 where we've been talking about least squares regression. And in this video we'll talk about interpreting the slope and y-intercept of the regression line. Now, we'll continue to refer to the age cholesterol study that we've used in previous videos. In this data set, recall that we had the age and total cholesterol for 14 women aged 25 to 65. We fit a least squares regression model to that data and got the regression equation predicted total cholesterol equals 151 plus 1.40 times age. Now, in our last video, we saw how to use this regression equation to predict the total cholesterol given any woman's age between 25 and 65. But in this video, we want to discuss the interpretation of the slope and intercept terms in the regression model. So the interpretation of slope is this. As the x variable increases by 1 unit, the y variable either increases or decreases by blank units. And what goes into the blank is the absolute value of the slope coefficient. And when we say that the y variable either increases or decreases, well, that depends on the sign of the slope. If the sign is positive, then the y variable is predicted to increase as x increases. If the sign on the slope is negative, then the y variable is predicted to decrease as x increases. So let me say this one more time. As the x variable increases by 1 unit, the y variable increases or decreases by blank units. Now, let's apply this to our cholesterol model. Our regression equation is predicted total cholesterol is equal to 151 plus 1.40 times age. So we interpret the slope by saying, as age increases by 1 year, total cholesterol increases by 1.40 in its milligrams per deciliter. So again, we'll say, as age increases by 1 year, total cholesterol increases by 1.40 milligrams per deciliter. Now let's look at another example. This is a data set from your text where a professor has taken a sample of students and plotted their final grade averages versus their number of absences. She fit a least squares regression model to this data and obtained the regression equation predicted final grade average is equal to 88.7 minus 2.8 times the number of absences. So again, we say that the interpretation of slope is that as the x variable increases by 1 unit, the y variable either increases or decreases by blank units. Now in the case of our last data set, where we have predicted final grade average is equal to 88.7 minus 2.8 times the number of absences, our interpretation of the slope is, for each additional day absent from class, final grade average decreases by 2.8 points. For each additional day absent from class, final grade average decreases by 2.8 points. Why does it decrease? Because the sign on our slope is negative. So as the number of absences increase, final grade average tends to decrease. So now, let's talk about interpreting the y-intercept. The y-intercept is the value of the response variable, that is the y, when the explanatory variable, that is the x, is 0. Again, it's the value of the response variable when the explanatory variable is 0. Now it's important to realize that it may not be sensible to provide an interpretation of the y-intercept in a given problem. To interpret the y-intercept, we first need to ask two questions. First, is 0 a reasonable value for the explanatory variable? And then if it is, we ask, do any observations near x equals 0 exist in our data set? And if the answer to either one of these is no, then the y-intercept is not interpretable in our problem. So let's think back to our cholesterol data. We had a regression equation of predicted total cholesterol is equal to 151 plus 1.40 times age for women between 25 and 65 years old. Now, the intercept term is 151. Can we provide an interpretation of this value? Well, the model says that our predicted total cholesterol is going to be 151 when age equals 0. Now let's ask, is 0 a reasonable value for age? Well, I suppose it is. We could think about the ages of babies less than 1 year old close to 0. However, we don't have anyone in our data set even close to 0 years old. The youngest people in our data set are 25. And so our regression model was calculated, of course, based on this data. So it doesn't make sense to provide an interpretation to our intercept term for this regression model. Now, let's think about our test score data. Our regression equation is predicted final grade average is equal to 88.7 minus 2.8 times the number of absences. Now the intercept term is 88.7. And so our regression model predicts that a student's final grade average is going to be 88.7 if she had 0 absences. And so now we ask the question, is 0 a reasonable value for the number of absences? Well, of course it is. And further, we have one student in our data with 0 absences, and we have other students in our data with nearly 0 absences. So it is reasonable to provide an interpretation of the y-intercept for this model. We'd say the y-intercept term is 88.7. We predict that students with 0 absences will have, on average, a final grade of 88.7. Now, two last cautionary notes. First, if the least squares regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, we say the researcher is working outside the scope of the model. So our cholesterol data is a good example. This regression model was based on women between the ages of 25 and 65. Now, we don't know that the linear relationship we're seeing here would continue for women younger than 25 years old or older than 65. In fact, I suspect this linear relationship we're seeing here would change if we had data on ages that were either very young or very old. But the point is that we can't use this model to extrapolate outside the range of values in our original data. And so this is our last cautionary note. Never use a least squares regression line to make predictions outside the scope of the model because we can't be sure the linear relationship we're seeing continues to exist. This is called extrapolation. But when we use values that are inside the scope of the model, that is the domain of our original x values, then predictions are safe to use. Predicting within the domain of the explanatory variable is called interpolation. So, this brings us to the end of section 4.2. There was a lot of information in this section, so you want to go back and read through pages 209 to 216 in your text. There's an example in this section that involves predicting the driving distance of a golf club as a function of the speed of the club head. And we recommend that you work through that example doing the calculations in either Minitab or StatCrunch or both. And then we recommend that you try the problems shown here beginning on page 218 of your text. And don't forget that the odd-numbered problems are worked out in the Student Solution Manual, which can be found on Course Compass under the Tools for Success tab.